Okay, so our next talk continues on Grape Eclipse data. In this case, the October 2023 event, the annular eclipse that passed by this fall. And this is Rachel Boedicker, AC8XY. Rachel's here at Case Western, and she's been working with Professor Frizzell here on some analysis of this event. And so Rachel will bring your talk up and give the floor.
Hello, everyone. I'm Alpha Charlie 8 X-Ray Yankee, or Rachel. I'm going to be talking a little bit about the Grape Eclipse data that was collected in October. So many of you in the audience probably helped collect some of this data, so it might not be news to you. Oh, there we go. Okay, so just in general about solar eclipse, during the daytime we usually have a lot of solar radiation blasting the ionosphere. During a solar eclipse, we have a sudden occultation, or basically kind of a localized night. So for the eclipse paths coming in for 2023 and 2024, we had proposed the NSF grant to have a series of Grape stations added to the original Grape Classic network. And this is what we ended up with during the 2023 eclipse. So in blue, we have the classic Grape stations that we still had recordings from, and we also have Grape 1 stations recording in digital RF data, which is spectral data. And for reference, the path of the eclipse. Okay, so we had a few questions also from the initial proposal that you heard last HamSCI, hopefully. For this case, we don't necessarily want to focus on general dawn-dusk or general response, and we also can't necessarily talk yet about how two eclipses might compare, because we haven't recorded two eclipse datas. Check back after April 8th. But for the general questions, we can talk about how similar the eclipse is, or just the annular eclipse, so not a full covering, but where there's still a little bit of light, is to the daily dawn-dusk terminator passage. We can ask how the ionospheric response might be symmetric or asymmetric, and we can also look at multipath mode splitting, specifically with the DRF data. So this is a typical example of DRF data. It's full spectral, it's 5 hertz on either side, but it gives us a much better picture of what's going on than just Grape 1 data classic. For reference, this is, although you just sat through talk on this, this is kind of what Grape 1 classic data looks like. It's Doppler data, but it's mostly looking for the maximal frequency that's being received at that point, at any given point, whereas the spectral data gives us a little bit more information, which shows us situations where there might be multiple paths that the signal is taking through the ionosphere, and therefore getting Doppler shifted by different amounts and being received at the same time. So this is really evident during dawn. So in the first main curve we have here with all of the splitting is a dawn signal. And then we have the eclipse signal, which looks vaguely night-like, but it's not as intense. And there is a question on whether or not the total solar eclipse, since it will block out more of the sun, will have a more intense effect than the annular eclipse. At the moment, there's obviously a distinct difference between dawn and the eclipse signature. It's not really a full localized nighttime. The atmosphere doesn't have enough time to revert to kind of a nighttime state. This kind of curve, though, where we see the negative Doppler shift and positive Doppler shift over the course of the eclipse. So layers fall out, and then after the sun comes back, the layers reforming and causing that Doppler shift. Oops. Oh, I can actually highlight stuff in this mode. Oops. Appears on multiple signals. We have kind of a very classic curve set. I can't go back, though. So we have a couple signals here. Oops. From Kentucky and from North Carolina. And you'll notice there is some variation in how much other spectral spreading there is around that eclipse signature. In general, it's not very much more than the eclipse or from the dawn signature. If we take a closer look at that signature, we see that there is a lot more spectral spreading, depending on how much zero padding you use in your spectrum plot. You get more or less of those top features. But we do have a very recognizable scaled S-curve. Let's see, how am I doing on time? During the grape data. Oh. Are these out of order? Or maybe not. The other thing we can look at is multipath. So this one I highlighted specifically because it's got a slightly better broken up signature, so it's not just spreading, but we can kind of look into the actual signal and see that there's probably more definitive multipath. So signals may be taking a different path in the ionosphere that we can see a little bit more clearly, especially if we bump up the contrast. So we do see that there's some similarity between dawn and dusk in terms of that there can be multipath during the eclipse signal, but it's definitely not as intense or as necessarily as many layers as we get during the full kind of dawn situation. And then the last thing to note from previous talks is we still get certain amplitude drop-off periods in Grape 2 data as well, if you're watching for it. Okay. Mandatory disclaimer. I think I probably went way too fast. Does anyone have any questions on the data? I know I did go way too fast. I guess, if there are no questions.
Thanks, Rachel.
20 minutes
No.
Is it?
It is not possible for us to be ahead of schedule. This is a scientific conference.
Ahead of schedule.
Yeah. We're 20 minutes ahead of schedule, unless I have it wrong on here.
Wow. No, wait a minute.
But we started early.
Did it?
We started early.
But we're 20 minutes ahead of schedule. So we should, dialogue.
Okay. So, and do we have a... Bill, you were pointing at something. Oh, we have a question. Daniel, can you...
Schedule, I'll throw out just because the longer thing is. So the ones where there's clear multipath,
Right.
how distinctive do you think the angle of arrival of those different paths of the site is? Is that something you could potentially actually pick out with the phased array?
Okay, so just to repeat the question for the people online, Daniel Sheen is asking, with cases of multipath, are those different angle of arrival signals kind of overlapping with each other, and how much could one theorize about that, I suppose, for events like this?
Do you mean like for the separation for the multipath features?
I'm wondering if there's an interesting imaging experiment to be had here.
The imaging experiment would be kind of interesting, but like the separation of signals on a spectrogram would be very complicated. I'd probably have to turn to machine learning to do it.
I think that's a really interesting question, asking, how does the angle of arrival differ? And I think one thing that's, I see some comments. One thing, I don't think our current grape system is really set up to measure that. However, that is certainly something we could work into, but maybe that would be something that, sometimes people ask why, if we have one person running a grape in a particular town, why would we have two people running a grape in a particular town? This might be a good, reason to run these, multiple stations.
Right, and before I go to yet another question here, I will also mention that one of the challenges for a system like this is you often wonder about multipath from a local single station. But if you have multiple stations measuring in a sort of smaller area, you can start to sort of disentangle some of that. David, you had a question.
Yeah, I wanted to say that we have experience in this regard.
Right. I was going to actually point out that the New England grape cluster is really useful specifically for that and for TID look-like appearances, because you can look at a very controlled resolution area of the atmosphere.
But I'm not talking about that.
I know,
No, no,
it was
that
previous.
was the previous
yeah.
question. Go ahead, David.
What I'm talking about is we at Dartmouth have been measuring angle of arrival on signals of this sort for auroral emissions using imaging arrays, say 50 meters spacing between antennas. This is why I've been pushing for the space weather system to have multiple channels synchronized so that we can actually do this sort of imaging and get an idea of angle of arrival on these signals and be able to maybe parse what we're seeing.
Right.
Is the imaging done with interferometry?
Okay, so
Yes.
Yeah.
Yeah, essentially interferometer. We've mostly done 3 antennas, 4 antennas in a closely spaced array. We've done up to 17. But actually, this is also a reason to have the GPS-locked receivers, because you can set up an interferometry array with multiple receivers with people at different locations.
Right. Continuing, Bob, go ahead.
Are you zeroing out the phase or just letting it be random?
David, maybe you guys could
Yeah, we'll go off.
talk about that. Yeah, but because we're going way down into the details. Other questions that on Rachel's talk are related subjects, since we have a moment or two?
Yeah, real quick.
Oh, yes, go ahead.
Rachel, the last slide, you showed those strong, sort of semi-periodic dropouts right there.
Yeah.
What's the physical basis for those?
Well, in theory, it would be when I think the talk right, wait, how many before this?
I was going to ask you,
Yeah.
that's the same sort of thing as...
I thought,
That is the same thing.
yeah. Yeah,
Yeah,
it was
that's-
at 10:50. But I
Right.
assumed it was right before it, was just what I was kind of referencing. But the Grape 2 still exhibits the same kind of MUF dropouts, and therefore sudden amplitude changes for certain stuff.
You can map one of these charts up against the FL-Digi amplitude, and they match them almost exactly.
Right.
Right, which is
Every time.
good news for both systems.
One more discussion point, and then I think we'll move. Oh, yeah, go ahead, Gwen, and I'll repeat.
Have you been able to identify the frequency spread of 1 hop and 2 hop propagation, and when you have mixed 1 and 2 hop? And have you also considered, for this case, 2 hop side scatter?
Right. I don't know if we're necessarily considering hop, because the only thing we get is received Doppler. So we can tell when there's a separated...
The of the Doppler, the thickness of the trace that you
Yes.
see on those graphs.
At the moment, not as much heavy analyzing on the spectral data, just because, so it's technically 3-dimensional data, so it could be done by treating it as an 3-dimensional data and considering the peak in the time dimension and then fixing widths and stuff. But at the moment, I haven't done that yet.
Sure. It's Steve Serwin. Are you here somewhere? Steve, you've been looking into some similar of these subjects. I don't know if you want to make any comments here before we move on.
I've been studying this for several years. I've got a number of different...
They're bringing a microphone.
Yeah. They don't want to hear me repeat what you're saying.
I've studied these mode splitting, I've been calling it, for several years. I've done mathematical analyses. Doppler, you know, is the time derivative of path length change. So you can have 1 hop, 2 hop, and 3 hops. Each of those paths is longer than the one before it because it makes more up and down motions, but they're all set by the height of the layer. So as the layer height changes height, the longer path has more path length change than the 2-hop mode, than the 1-hop mode, but it all happens in the same time. So I believe that the splitting that we see is caused by the different rates of path length change caused by the number of hops. And to prove that, I've taken some of the Doppler data, which again is the derivative of height, done a part-by-part integration of it to get back to height, and reconstructed the change in height from night to day that you see on an ionosonde. They match pretty close. I've also done the inverse thing, taken that ionosonde curve, which is high at night, big slope as the sun comes up, and then the lower daytime height. Take the mathematical derivative of that curve and feed it through the formulas for 1 hop, 2 hop, 3 hop, and you will reproduce very closely those curves, something that looks very, very similar to it. So I think that mode splitting happens because of the differential rates of change of 1 hop, 2 hop, and 3 hop modes.
And Steve, I would say, you've made prior presentations on that at HamSCI as well. So, there's material that Steve either could see or you can find through the workshop as well, if you want to dig in. Thanks, Steve. I thought that was important context.
And he has posters tomorrow, too.
Yes, and we just got reminded Steve has a poster tomorrow, so guess where you're all going to start with. All right, Rachel, thank you very much. This was great.
I think we could still delay a little longer.